Hey there, everyone. Good morning. The first problem this week involves no calculations whatsoever. Everything is completely symbolic here. We have a truck that's sliding down an icy road, and we need to apply energy conservation to figure out how far up it will go on this nearby ramp. It's not super hard, but it's one of those problems that we'll have to break into stages, because the final velocity at the bottom of the road becomes the initial velocity at the beginning of the ramp. So let's go ahead and split this picture in half. The first part we'll call stage 1 and the other stage 2. Before we do anything with energy, notice that we weren't provided any kind of height for the truck in either stage. That's going to be a problem, since we need that for our potential energy. Let's grab it in stage 1 first. If we want the initial height in stage 1, we're going to need the definition of the sine function. Let's plug in the quantities for our problem into that definition, like this. We can isolate the initial height on the right-hand side by multiplying both sides by the length of the road, capital L. And that's all it takes. When it comes to the energy conservation of stage 1, there's a couple things that can be eliminated. There's zero friction while the truck slides down this icy road, so the other work in this part is 0. If we call the bottom of the road y is equal to 0, then that would mean there's no potential energy at that point. Nothing else can be reduced here, so let's go ahead and grab the definitions for these. Notice there's a mass variable in every single term. Let's divide that out and get rid of it. We can also plug in the trig expression for the initial height, like this. If we multiply both sides by 2, then what's left is the square of the final speed of stage 1 on the right-hand side. Hang on to that for the time being. We'll need that for later. Let's shift our focus over to stage 2 now and get the final height out of the way. The process is exactly as we saw before. You start with the sine definition, then plug in the provided quantities, and multiply both sides by the length of the hypotenuse. A free body diagram is also going to be necessary here, so let's draw one up real quick. The forces acting on the truck as it moves up the ramp will be its weight, the normal force provided by the ramp, and rolling friction acting opposite to the truck's movement. Since the weight doesn't lie along the y-axis, we'll break it down into components and insert our ramp angle to get the cosine and sine pieces. Now we're ready for energy conservation. The truck is at the bottom of the ramp in the initial portion of stage 2, so that means it won't have any potential energy there. We were also told that the truck will eventually come to a stop. Thus, our final kinetic energy will be 0 as well. Let's plug in the remaining parts. The square of the final velocity of stage 1 shows up again, here on the left, which means we can plug in that expression we had for it from earlier. Another thing we can do is exchange the rolling frictional force with mu sub r times the normal. As we saw in the free body diagram, the normal was being balanced out by the cosine portion of the weight, so that part can go in next. Let's also rewrite the weight as mg. Things are getting a little long here, but we can eliminate a factor of mass from both sides, like before. The goal is to get an expression for x, so let's get both x terms over on the right-hand side, like this. I'll factor out x, but notice there's a g attached to both terms inside the parentheses as well. Let's pull that out too. If we distribute the 1/2 here on the left, then divide both sides by g, then divide both sides again by the sum of these trig identities inside the parentheses on the right, then we're done. That's it. Problem solved. I hope this helped. Thanks for watching.